These spheres, only about the size of a city, look small and silent, easily forgotten. Yet magnetars are anything but safe. They are the most extreme magnetic objects in the known universe. Their magnetic fields are powerful enough to strip electrons from atoms and bend the path of light, and a single eruptive release of energy can exceed the total radiation of the Sun over 100,000 years. They are born from the death of massive stars, stretching the laws of physics to the point of breaking. This is a long story, but before we dive in, remember to like and share. If a magnetar were to unleash its full fury near Earth, we would likely never have the chance to tell this story at all. Every magnetar is born from a catastrophe, starting with a massive star 8 to 20 times the mass of the Sun. It burns through its fuel in a violent and brief existence, fusing hydrogen into helium, then carbon, and moving down the periodic table until it reaches iron. When iron fusion begins, the process stops producing energy, and gravity finally wins. In less than a blink of an eye, the core collapses inward under incredible force, squeezing more mass than the Sun into a sphere only 20 kilometers wide. This is how a neutron star is born. A typical neutron star is a city-sized object so dense that a single teaspoon of its material would weigh as much as a mountain. But magnetars are the rarest and most extreme members of this family. Only about 1 in every 10 neutron stars becomes a magnetar, suggesting something extraordinary happens at the moment of their birth. While ordinary neutron stars spin fast and carry strong magnetic fields, a magnetar requires conditions far beyond the norm. The magnetic fields of these stars can reach 10 to the power of 14 or 15 Gauss. This strength is enough to tear atoms apart, creating an energy density comparable to the most extreme environments in the early universe. The question is how a collapsing star avoids becoming a normal neutron star or a black hole and instead creates a magnetic monster. Astrophysicists suspect the key lies in two factors: ultra-fast rotation and dynamo amplification. Conservation of angular momentum causes the shrinking core to spin faster and faster, much like a figure skater pulling in their arms. If the rotation period is as short as a few milliseconds, the differential motion between internal layers can trigger a dynamo effect. The principle is similar to how the liquid metal in Earth's outer core generates a magnetic field, but the scale here is unimaginable. Dense matter spinning hundreds of times per second at temperatures over 1 trillion Kelvin creates convective flows that amplify a weak magnetic seed into a colossus. Within seconds, a magnetic titan is born. Observations support this idea. Magnetars seem to favor massive progenitor stars that leave behind compact, rapidly spinning cores before losing their angular momentum. Some are found in clusters of young, massive stars, suggesting their ancestors were short-lived and ended in supernovae or even hypernovae. Gamma-ray bursts are also a signal. These are among the brightest explosions in the universe, some lasting only seconds yet outshining entire galaxies. Some models link long-duration bursts to the rapid rotation of a proto-magnetar, where the spin is converted into magnetic energy and relativistic winds that drive intense radiation until the star slows down or collapses into a black hole. In this pathway, magnetars are not just stellar remains, they are the engines behind some of the most dramatic events in cosmic history. Supernovae themselves can carry this magnetic fingerprint. When astronomers observe superluminous supernovae, which are 10 to 100 times brighter than typical ones, magnetic engines often appear in the theoretical models. A newborn magnetar spinning down through magnetic braking injects rotational energy into the expanding debris, keeping it hot and bright far longer than radioactive decay alone could explain. The light curves of several superluminous supernovae match this magnetar power scenario, suggesting we have witnessed the birth of magnetars across the universe. The birth is violent and not yet fully understood. In less than a second, the core shrinks from thousands of kilometers to dozens. Neutrinos, nearly massless particles, pour out in a flood, carrying away most of the gravitational binding energy. This flood cools the proto-neutron star and drives a shock wave through the outer layers. If the shock is strong enough, the explosion succeeds. If not, the material falls back and crushes the core into a black hole, ending the Magnetar story before it begins. For the survivors, the first few minutes are critical. Internal convection stirs the hot, neutron-rich matter while differential rotation winds the magnetic field lines tighter and tighter. If the dynamo is efficient, the field grows exponentially, reaching quadrillions of Gauss in seconds. At this point, magnetic pressure rivals the internal pressure of gas and radiation, shaping powerful winds and even altering the structure of the surrounding supernova remnant. These early winds may also be rich in heavy elements. Gold, platinum, and uranium could be synthesized through rapid neutron capture on seed nuclei. Whether magnetars play a major role in the cosmic abundance of these elements is still debated, but their high entropy and intense neutrino flux make them prime candidates alongside neutron star mergers. When we talk about magnetic fields on Earth, we think of refrigerator magnets or the medical scanners that use magnetic resonance. Earth's surface field is about half a Gauss, and even the strongest steady magnets in labs only reach tens of thousands of Gauss. Most neutron stars have fields around a trillion Gauss, but magnetars push this to a quadrillion. At this scale, magnetism does more than just move objects, it rewrites the rules of atomic physics. Normally, an atom is shaped by the balance between the attraction of the nucleus and the quantum mechanical spreading of electrons. In a magnetar's field, magnetic pressure crushes the electrostatic forces. Electron orbits are compressed perpendicular to the field and stretched along the field lines into thin cylinders. The electron cloud is no longer spherical but needle-like, with an aspect ratio that can exceed 100 to 1. Calculations show that once the field exceeds a billion Gauss, atoms begin to deform. Near a quadrillion Gauss, the binding energy of electrons skyrockets, changing surface chemistry and how radiation escapes. The influence extends beyond atoms to the vacuum itself through quantum electrodynamics. Normally, vacuum is linear, meaning light waves pass through each other without interference. But near the Schwinger limit, the vacuum becomes nonlinear. Virtual electron-positron pairs constantly flicker in and out of existence, pinned by the magnetic field, causing the empty space to act like a birefringent crystal that splits light into different polarizations. Magnetars exist far beyond these limits, making them natural laboratories for theories from the 1930s. These fields can even pull matter directly from the vacuum. When magnetic energy density exceeds nuclear binding energy, it triggers a cascade of particles and photons, filling the magnetosphere with a dense plasma that feeds radio bursts and high-energy radiation. Essentially, the magnetic field becomes an engine turning energy into matter and light. Near the surface, magnetic pressure competes with gravity. The crust, already the densest solid in the universe, endures massive magnetic stress. Over centuries, it is slowly twisted until it suddenly snaps in a starquake. These fractures violently rearrange the magnetic field, releasing stored energy as a giant flare. The 2004 flare from a magnetar 50,000 light-years away was briefly brighter than every other gamma-ray source in the sky combined. If such an event happened within 10 light-years, our ozone layer would be stripped away, causing a catastrophe for life on Earth. In these environments, even the fine structure constant, which governs electromagnetic interactions, sees its effects modified. The behavior of matter under this compression and radiation is an area where theory is still being perfected. Deep inside, the density exceeds that of an atomic nucleus, and matter may turn into a neutron-rich fluid or even quark matter. Strong fields quantize the motion of particles into Landau levels, altering the equation of state that controls pressure and density. Beneath the blinding X-rays and massive magnetic fields lies a seemingly ordinary layer of solid crust. It is only about 1 kilometer thick, covering a star 20 kilometers in diameter. Compared to the forces raging beneath it, the crust seems fragile, yet it is vital to the magnetar's life. It acts as a shield, isolating the internal superfluid from the magnetic pressure building up over years or centuries. When it reaches a breaking point, a starquake occurs. One quake can shake the entire star, equivalent to the energy of billions of nuclear bombs. To understand why, we must look at what this crust is made of. After a supernova, the outer layer cools into a lattice of atomic nuclei submerged in a sea of relativistic electrons. The density increases sharply with depth. The surface might be 10,000 times denser than lead, but just meters below, it exceeds nuclear density. Here, protons and neutrons begin to dissolve into exotic states. The outer crust is mostly iron-like nuclei, while deeper down, the pressure forces electrons to merge with protons, turning them into neutrons and creating a region where nuclei coexist with a sea of free neutrons. The magnetic field is the key ingredient here. It runs through the entire star, including the crust and core. As the interior cools, processes like Hall drift and ambipolar diffusion drag magnetic footprints through the solid crust, winding up stress. Imagine bending a stick a little more every day, eventually, it snaps. Magnetar crusts behave the same way but on a cosmic scale. During these events, the entire neutron star rings like a bell. The oscillations detected in the aftermath of flares are echoes of these waves traveling through the solid layer, providing a rare opportunity for stellar seismology. The crust also manages the exchange of heat and angular momentum. Superfluid neutrons inside rotate as quantum vortices, while the crust rotates rigidly. Sudden jumps in rotation, known as glitches, occur when these two regions suddenly exchange momentum. In magnetars, these glitches often happen alongside bursts, suggesting they share a common origin. When a magnetar reaches the end of its centuries-long internal struggle, it vents its fury in a starquake. When the magnetic stress exceeds what even the strongest material in the universe can bear, the crust and magnetic field lines snap and reconnect. Energy turns into radiation, particles, and seismic waves. The scale of this destruction is nearly impossible to imagine. The largest flares from our Sun release incredible energy, but a magnetar giant flare can release as much energy as the Sun produces in 100,000 years, all in a single blinding flash. This process starts slowly, with the magnetic field leaving twisted marks in the crust over decades. The crust resists like steel until it hits a catastrophic limit. Once it begins, cracks race across the surface at millions of meters per second. Magnetic lines snap and reconnect like solar flares but 10,000 times larger, accelerating particles to near the speed of light. To us, this appears as a massive flash of gamma rays and X-rays. The most famous flare occurred in December 2004. In just 0.2 seconds, it released energy equal to the Sun's output over 100 millennia. Satellites were blinded, and the radiation was strong enough to alter Earth's ionosphere even after reflecting off the Moon. This is a sobering reminder of what would happen if such a star were closer. These flares have a specific structure, a sharp initial spike carrying most of the energy, followed by a fading tail that pulses as the star rotates. Astronomers have recorded 3 confirmed giant flares in or near our galaxy, in 1979, 1998, and 2004. Many more are suspected in other galaxies, often disguised as short gamma-ray bursts. Some even speculate that certain isotope spikes in Earth's history could be linked to nearby magnetar events. To understand how unique magnetars are, compare them to common neutron stars and pulsars. While all are born from collapsing stars and spin rapidly, magnetars are the extreme outliers. Comparing them to a normal neutron star is like comparing a hurricane to a gentle breeze. The excessive strength of these magnetic fields creates a massive rift in observable behavior. While common pulsars radiate primarily through the loss of rotational energy, slowing down over millions of years to provide radio beams and X-ray pulses, magnetars are primarily powered by the decay of magnetic energy. Their continuous X-ray luminosity far exceeds what their slowing rotation could possibly supply. In other words, a pulsar is like a slowing flywheel, while a magnetar is a magnetic battery discharging its energy through short bursts, giant flares, and steady heating. Rotation also marks a significant divide. Many young pulsars spin more than 100 times per second. For example, the Crab pulsar still spins at about 30 revolutions per second after nearly 1,000 years. In contrast, magnetars rotate very slowly, with common periods between 2 and 12 seconds. This was puzzling until we realized their immense magnetic fields act as an incredibly efficient brake, dragging against the magnetosphere and slowing them down in just a few thousand years. Their aging process is equally distinct. While ordinary pulsars can remain active for tens of millions of years, magnetars live fast and die young. Most known magnetars have characteristic ages of only tens of thousands of years. Eventually, their magnetic fields decay until they can no longer drive giant flares, leaving behind quiet neutron stars that may appear as dim, isolated objects. Their radiation behavior further deepens the contrast. Pulsars are the reliable metronomes of the universe, with predictable slowdowns rarely interrupted by glitches. Magnetars, however, are addicted to the unpredictable. They exhibit short bursts, long-term X-ray eruptions, and even anti-glitches where rotation suddenly slows. Their intense fields twist the magnetosphere into unstable structures where even a tiny shift in the crust can trigger a reconnection avalanche, releasing energy levels a pulsar could never reach. The surface of a magnetar is a realm of extreme physics where the magnetic field suppresses heat conduction in certain directions, creating hot spots at the magnetic poles. The atmosphere itself might even condense into a metallic solid rather than remaining a gas, fundamentally changing how X-rays escape. Deep inside, the magnetar may be even more alien. The super-strong field likely causes the star to deviate from a perfect sphere. If this asymmetry persists, it could radiate gravitational waves. While superconducting protons and superfluid neutrons create strange magnetic dynamics in ordinary neutron stars, the intensity of a magnetar pushes these states into unknown territory. The evolution of a magnetar is a war between rotation and magnetism. A newborn neutron star often inherits the angular momentum of its parent star, spinning hundreds of times per second. Initially, this rotation dominates the energy budget, acting like a cosmic generator. But over time, the magnetic field drains this energy. The spinning magnetic field acts like a giant antenna, radiating energy outward and dragging plasma into a wind that carries away angular momentum. The stronger the field, the faster the brake. A pulsar takes millions of years to slow down, but a magnetar burns through its rotational energy in a few millennia. Mathematically, the energy loss is proportional to the square of the magnetic field and inversely proportional to the cube of the rotation period. Early on, a fast-spinning magnetar might power superluminous supernovae, but this phase is brief. As the period grows to several seconds, magnetic energy takes over. This slowdown isn't always smooth. When angular momentum is transferred between the crust and the internal superfluid, glitches occur. The crust slows down due to magnetic braking, but the frictionless superfluid lags behind until quantum vortices suddenly unpin, dumping momentum back into the crust and causing a sudden jump in spin frequency. As rotation slows, the light cylinder radius expands. In ordinary pulsars, this eventually kills the radio mechanism, pushing them across the pulsar death line. Magnetars cross this line quickly but remain active because they rely on magnetic decay. Over tens of thousands of years, processes like Hall drift and ambipolar diffusion rearrange and dissipate the magnetic field. As the field weakens, X-ray luminosity drops, giant flares become rare, and the magnetar fades into silence. Some theories suggest that the initial spin rate at birth determines whether a neutron star becomes a magnetar at all. If the proto-neutron star spins fast enough, a dynamo mechanism amplifies the magnetic seed to magnetar levels. If not, it becomes an ordinary pulsar. Above the surface lies the magnetosphere, a vast, invisible cage woven from magnetic field lines where particles race at nearly the speed of light. Imagine the Earth's magnetosphere with its dipole lines and auroras, then multiply that scale by a trillion. A magnetar's field locks plasma into rigid structures, blurring the boundary between matter and magnetism. Unlike the open field lines of a pulsar that produce steady radio beams, a magnetar's magnetosphere is filled with currents and twists. As the crust shifts, it drags the magnetic footprints, twisting the field lines like rubber bands. The more they twist, the more energy they store, and the more unstable the system becomes. These twisted regions trap high-density electron-positron pairs, setting the stage for magnetic reconnection that can clear out stored energy in milliseconds. The physics here is beyond anything we can recreate on Earth. In these fields, the vacuum itself becomes polarized, and quantum electrodynamics effects dominate. Photons can split or transform into pairs of matter and antimatter directly from the void. These twisted field lines also heat the surface, as particles accelerated along the lines strike the crust, creating hot spots that emit thermal X-rays. During active periods, X-ray luminosity can skyrocket and stay high for years. While the star is only 20 kilometers across, its closed magnetic loops can extend thousands of kilometers. Some magnetars even briefly turn into radio pulsars after an X-ray burst, showing that the magnetospheric reconfiguration can temporarily create the right conditions for radio emission. In the everyday world, light travels through a vacuum without being bent or split. But near a magnetar, the concept of empty space collapses. When the field exceeds the Schwinger limit of about 44 trillion Gauss, the vacuum is filled with virtual electron-positron pairs that align with the field. This causes vacuum birefringence, where light is split into different polarizations traveling at different speeds, much like light passing through a crystal. Magnetars are the only natural laboratories where this becomes a dominant reality. Observations from telescopes like the Very Large Telescope and the imaging X-ray Polarimetry Explorer have begun to capture evidence of these QED effects, such as highly polarized light that cannot be explained by interstellar dust alone. This magnetic vacuum also allows for photon splitting, where a single high-energy gamma photon splits into two lower-energy ones. This softens the energy spectrum of magnetar flares and limits the escape of the most energetic photons. Furthermore, a single photon can transform into an electron-positron pair without hitting another particle, as the magnetic field provides the necessary momentum. These processes fill the magnetosphere with a dense plasma fireball. In a giant flare, this plasma can become so thick it is opaque to its own radiation, trapping light until pressure pushes it out in a relativistic explosion. Magnetars may also be the ultimate particle accelerators. When the energy of cosmic rays reaches the limits of what we can detect, we look for the most violent engines in the universe. A spinning magnetar creates a massive potential drop across its open field lines, reaching quadrillions of volts. For comparison, the Large Hadron Collider only reaches trillions of volts. Magnetars could theoretically accelerate protons or heavy nuclei to the highest energies ever observed. While direct evidence is still being gathered, the arrival directions of the most energetic cosmic rays seem to correlate with galaxies active in star formation, where magnetars are most likely to be born. Whether through unipolar induction or magnetic reconnection in the twisted magnetosphere, magnetars stand as unique candidates for the universe's most powerful accelerators, turning pure magnetic energy into the fastest moving matter in existence. Shockwave acceleration occurs at the front of relativistic outflows as they collide with the surrounding medium. Some particles escape to become cosmic rays, while others remain trapped, radiating synchrotron emission along magnetic field lines. Near the surface, gamma radiation can trigger pair cascades, further altering the magnetosphere and creating persistent emissions. While gamma-ray telescopes currently identify magnetars through short bursts rather than steady output, the aftermath of a giant flare may produce secondary cosmic rays and neutrinos that reach Earth millions of years later. Magnetar flares have been proposed as a source for high-energy neutrinos detected by IceCube, though definitive proof is still lacking. If magnetars truly accelerate cosmic rays to extreme energies, they must face the GZK cutoff, where particles lose energy by interacting with cosmic microwave background photons. Consequently, any such ultra-high energy particles we observe must originate from neighbors within 100 million light-years, where magnetars in nearby galaxies or our own Milky Way could be the culprits. Before the term magnetar existed, astronomers were baffled by soft gamma repeaters. Unlike one-off gamma-ray bursts, these sources erupted repeatedly from the same spot for months or years. They seemed to be cosmic engines capable of storing energy for decades and releasing it in waves. The breakthrough came on March 5, 1979, when multiple spacecraft recorded a massive gamma-ray flash shorter than a second, followed by a pulsating tail with an 8-second period. This periodicity revealed a rotating object in the Large Magellanic Cloud. Over the next decades, sources like SGR 1900+14 and SGR 1806-20 were identified, each capable of flashes far exceeding ordinary stellar flares. The repeatability ruled out one-time catastrophes like core collapse, leading models toward unstable neutron stars with magnetic fields exceeding 100 trillion Gauss. The magnetar model suggests internal magnetic fields twist the crust until it fractures, triggering reconnection in the magnetosphere. This accelerates floods of electron-positron pairs, pushing gamma rays into space. Each burst relieves stress, which then slowly rebuilds for the next eruption. In April 2020, the galactic magnetar SGR 1935+2154 emitted an X-ray burst simultaneously with a millisecond radio flash, directly linking at least some fast radio bursts to magnetar activity. While not all FRBs may come from magnetars, they are now the primary suspects. These bursts, which can release as much energy as the Sun produces in days within a thousandth of a second, were first discovered in 2007. Magnetars are the only objects capable of producing such coherent, bright radio pulses across the universe. Magnetars do not live in isolation, they are surrounded by the debris of their birth. Their winds and flares carve out magnetized cavities in the interstellar medium, creating nebulae like the one seen after the 2004 giant flare. These environments are extremely hostile. A planet orbiting a magnetar would face a bombardment of X-rays and gamma rays capable of stripping an atmosphere and sterilizing the surface in an instant. Even if a planet survived the initial supernova, the magnetar's ongoing magnetic decay would subject it to storms thousands of times stronger than anything produced by our Sun. Induced currents from shifting magnetic field lines could melt a planet's crust and ionize its air. In this realm of high gravity and magnetism, mountains can form. On a magnetar, these mountains are only centimeters high, but because of the star's density, even a tiny bump creates a mass asymmetry. As the star spins, this asymmetry radiates gravitational waves. While these signals are too weak for current detectors like LIGO to see continuously, future observatories might capture the ringing of a magnetar after a starquake. These events link the deep interior physics where matter might exist as strange nuclear pasta to the observable flashes in the sky. The most violent part of a magnetar's birth isn't the light or the magnetic field, but the neutrinos. In the first seconds of core collapse, almost all the gravitational energy is released as a flood of these ghost particles. This neutrino storm is so intense that for a brief moment, it outshines all the stars in the visible universe combined. This thermal sea drives the shock wave that eventually explodes the star's outer layers, leaving behind the magnetic monster we call a magnetar. Energy levels at this scale can tear heavy nuclei into free nucleons. In the hundreds of milliseconds following core collapse, a protoneutron star pours out a flood of neutrinos and antineutrinos of all flavors, carrying away the bulk of the star's energy and lepton number. Unlike photons, which remain trapped for millions of years, neutrinos stream out almost instantly. For a magnetar, this process is reshaped by ultrafast rotation and extreme magnetism. A dynamo mechanism amplifies the magnetic seed to a quadrillion Gauss within seconds, twisting the field into a toroidal structure within the fluid interior. Meanwhile, neutrino-driven convection rolls the hot material, fueling both the magnetic growth and the neutrino torrent. In those first seconds, the protoneutron star emits a neutrino pulse totaling 10 to the power of 53 ergs, a luminosity exceeding that of the entire visible universe. If this neutrino heating succeeds in reviving the shock wave, the explosion is a success. If it fails, the material falls back and swallows the star into a black hole. This sea of neutrinos also sets the initial conditions for everything to follow, including the magnetic configuration and the formation of the crust. When the outer layers eventually solidify at temperatures below 10 billion degrees, they freeze the magnetic field in place, storing the energy for future starquakes and giant flares. Direct evidence for this neutrino flood came from SN 1987A, where detectors captured 24 neutrinos from a star over 160,000 light-years away. If a magnetar were born in our galaxy today, modern detectors like Hypercameo would allow us to watch the birth in real time, second by second, testing how extreme fields change the cooling and explosion dynamics compared to ordinary neutron stars. A newborn magnetar is unimaginably hot, with core temperatures exceeding 100 billion degrees, enough to vaporize nuclei into a uniform soup. However, the furnace cools rapidly as neutrinos carry away the binding energy. Within days, the crust solidifies, and superfluid states begin to freeze inside, setting the stage for thousands of years of thermal and magnetic evolution. While ordinary neutron stars cool primarily through neutrino emission followed by surface photon emission, magnetars rewrite this script. Their magnetic fields inject extra heat into the crust through ohmic dissipation and Hall drift. Consequently, magnetars are not just cooling, they are caught in a tug of war between cooling and magnetic heating. This explains why a 10,000-year-old magnetar remains at several million degrees, while a pulsar of the same age has cooled significantly. The extra heat comes from the magnetic energy stored in the shell, slowly dissipating over hundreds of millennia. The Hall effect moves magnetic energy nonlinearly through the dense electron gas, creating localized hot spots. Because this heat is distributed unevenly, many magnetars pulse as these hot spots rotate in and out of view. Some magnetars maintain steady heating, while others experience massive luminosity spikes during eruptions as starquakes inject heat into the outer layers. This cooling process also allows us to probe exotic states of matter. Above nuclear density, neutrons may pair into a superfluid, a transition that briefly accelerates cooling by releasing neutrinos before eventually suppressing further heat loss. In magnetars, we are still waiting for further observations to confirm how super-strong fields rewrite these phase transitions. When a magnetar releases the energy of 100,000 suns in less than a second, we must ask where that energy was hidden and what triggered the release. The answer lies in the magnetic field, twisted and stored within the crust over decades or centuries. As the internal currents rearrange themselves through Hall drift and ambipolar diffusion, they pull on the magnetic footpoints with an unstoppable force. Although the crust's shear strength is vastly superior to steel, it eventually yields when magnetic tension reaches 10 to the power of 19 dynes per square centimeter. The crust fractures, the footpoints shift kilometers in milliseconds, and the external magnetic field is twisted into an unstable topology, leading to a catastrophic reconnection. This triggers a flood of gamma rays, X-rays, and relativistic outflows. The 2004 giant flare from SGR 1806-20 remains a landmark event. In just 0.2 seconds, it outshone the entire gamma-ray sky, with an initial energy spike exceeding 10 to the power of 46 ergs. The pulsating tail revealed oscillations, quasi-periodic oscillations or QPOs, which are essentially the ringing of the star's crust and magnetic field in the aftermath of the quake. Whether the energy is stored primarily in the crustal tension or the twisted magnetosphere is still debated. The reality is likely a synergy of both. Slow movements in the crust wind up a magnetic spring in the magnetosphere until a global instability is reached. While giant flares make the headlines, magnetars also enter burst forests, periods where they release dozens or hundreds of smaller bursts within a few days. These storms release magnetic stress through multi-scale avalanches rather than a single global explosion. These bursts are often the first sign of life after years of silence, with individual flashes lasting less than a second but carrying immense energy. Statistically, the distribution of these burst energies follows a power law, a classic signature of self-organized criticality, much like terrestrial earthquakes. During these storms, we see heat from plasma fireballs and high-energy radiation from particles striking the surface. Following a storm, the X-ray pulse profile of a magnetar often changes completely, indicating that magnetic footpoints have moved and new hotspots have formed. In some cases, like the 2004 event, these storms act like pre-shocks that steadily push the system toward a global breaking point and the strongest flares ever recorded. This process is strikingly similar to solar flares, but on a scale where the physics is pushed to the absolute edge of relativity, quantum mechanics, and magnetic intensity. That concludes our exploration for today. I hope this deep dive into the magnetic monsters of the cosmos gives you plenty to think about. I wish you all a wonderful dream and a fantastic day ahead. We will see you in the next episode.